Hey folks, here in section 2.2 we're going to continue our study of limits. Specifically we're going to look at limits and asymptotes, vertical asymptotes and horizontal asymptotes. The objectives we're going to focus on in section 2.2 will be objective 1, analyze infinite limits and vertical asymptotes. And then in objective 2, we'll look at an application of infinite limits. Objective 3, analyze what are called limits at infinity and their relationship to horizontal asymptotes. And then in objective 4, we'll do an application of limits at infinity. So let's start things off by looking at this example. Here's the graph of f of x equals 1 over x. It's over here to the right. And we're going to use this graph to determine the following limits. Part A, the limit as x approaches 0 from the right of 1 over x. Part B, the limit as x approaches 0 from the left of 1 over x. And then part C, the limit as x approaches 0 of 1 over x. So you know the drill. Get this copied down into your notes. Because I'm going to head off to the board to work through this example. All right, folks, in this example we were given the graph of f of x equals 1 over x, and we were asked to find the limits. The limit as x approaches 0 from the right of 1 over x, the limit as x approaches 0 from the left, 1 over x, and then the limit as x approaches 0, 1 over x. So I'm going to go over there to the graph and let's try to analyze the first one. The limit as x approaches 0 from the right side of 0 of 1 over x. So, I start to the right of 0. I put myself on the graph, and I'm letting the x values get closer and closer to 0 from the right side. And as I do that, look what is happening. Those y values are getting larger and larger and larger. The closer I get to 0 from the right side of 0, those y values are getting larger and larger and larger. In fact, the y values are continually increasing. In fact, they're going to increase without a bound. There's no stop to how high they will increase. So we could say that this limit is increasing without bound, IWOB. It's increasing without bound. Now in mathematics, what we use to symbolize the concept that something is increasing without bound, we use the infinity symbol. It's not a number, don't treat it as a number, it's a concept. It means it's incredibly large. It's increasing without a bound. So we have that the limit as x approaches 0 from the right side of 0 of 1 over x is infinity. That limit is infinity. Well, now let's look at the limit as x approaches 0 from the left side of 0. So I come to the left side of 0 and I put myself on the graph and I want to get closer and closer and closer to an x value of 0 from the left side, and I'm looking at those y values. And it looks to me that when I get closer and closer and closer to 0 from the left side of 0, those y values are, well, they're decreasing. They're going to keep going on forever and ever and ever. They're decreasing without a bound. Or it's a DWOB. Decreasing without a bound. In mathematics, to communicate the concept that something is decreasing without a bound, we use the symbol negative infinity. Again, it's not a number, it's just telling you a concept. It's negative, and it's incredibly large negative, and it just keeps going on forever and ever. So we could write the limit as x approaches 0 from the left side of 0 of 1 over x is negative infinity. All right, that brings us to part C. What is the limit as x approaches 0? Well, keep in mind, in order for the limit, for us to talk about the limit, the left side limit and the right side limit have to be approaching the same thing. Well, the left side limit is heading to negative infinity. The right side limit is going to positive infinity. Those aren't the same thing. They are not approaching the same thing, so we conclude that the limit as x approaches 0 of 1 over x, it does not exist. Before we head back to the slides, I'm just going to point out one thing real quick. Notice that the y-axis, which has an equation of the form x equals 0, notice that that is a vertical asymptote for the graph of 1 over x. All right, let's head back to the slides and see what's next. All right, as we saw in that example, the limit as x approached 0 from the right of 1 over x was increasing without bound, but we used the infinity symbol to represent that. Likewise, the limit as x approaches 0 from the left of 1 over x, we said was decreasing without bound, and we used the negative infinity symbol to represent that. And since the left side limit and right side limit were not the same, in part C, we determined that the limit did not exist. So next, let's look at the graph of f of x equals 1 over x squared. So there it is. Use this graph to determine the following limits. Part A, the limit as x approaches 0 from the right, 1 over x squared. Part B, limit as x approaches 0 from the left, 1 over x squared. And then part C, the limit as x approaches 0 of 1 over x squared. So, I tell you what, get this written into your notes, pause the video, and you go ahead and do parts A, B, and C. And once you have done parts A, B, and C, restart the video, and I'll be at the chalkboard working through it, and hopefully you'll have it correct. All right, folks, this example, hopefully you did it. I asked you to pause the video and to try the example for yourself. You were given the graph of f of x equals 1 over x squared, and you were asked to find these three limits. So in part A, the limit as x approaches 0 from the right side of 0 of 1 over x squared. Well, I come to the right of 0, put myself on the graph, and I see as I get closer and closer to 0 from the right side of 0, I see that the y's are increasing without bound. That tells me this limit is infinity. For part B, the limit as x approaches 0 from the left side of 0, 1 over x squared. I come to the left of x equals 0, put myself on the graph, and I let my x's get closer and closer to 0. And as my x's are getting closer and closer to 0 from the left side of 0, I see that those y's are increasing without bound. So that limit is also infinity. For the limit, since the left-hand limit is infinity, the right-hand limit is infinity, the same thing, we conclude that the limit as x approaches 0, it too is infinity. And again, before we head back to the slides, I'm going to mention one more time for this one. Notice that the y-axis, also known as the line x equals 0, notice that it is a vertical asymptote for the graph. So let's head back to the slides and let's try to make this connection between these limits and vertical asymptotes. Well, as we saw in the first two examples, those limits were related to vertical asymptotes. Now, technically speaking, a line x equals a is a vertical asymptote of a graph of a function if any of the following are true. So the first thing, if x approaches a from the left side, the function values increase or decrease without bound. That is, the limit is infinity or negative infinity. Then x equals a is a vertical asymptote. If you approach a from the right side of a and the function values increase or decrease without bound, then x equals a is a vertical asymptote. And then if both the left-hand limit and right-hand limit exhibit the same behavior, increasing without bound or decreasing without bound, then we can say the limit exists and is infinity or negative infinity. So bottom line, that's technically what makes something a vertical asymptote. But what we're going to do is we're going to use vertical asymptotes to help us determine limits. So you may remember back to college algebra, there were times that a graph would have a hole in the graph, and there were other times you would have a vertical asymptote. So I'm just going to review what you should have seen in college algebra, and that is how to determine if a value of x is producing a hole in the graph or if it's producing a vertical asymptote. So first thing, determine all values that makes the denominator 0. Anything that makes the denominator 0 is doing one of two things: producing a hole in the graph or producing a vertical asymptote. So if a value that makes the denominator 0 also makes the numerator 0, in other words, it would be indeterminate form, there is a hole in the graph. And we can use algebra. We've seen how to determine the limit by using algebra. So anything that makes the denominator 0 and also makes the numerator 0 is producing a hole in the graph. On the other hand, if you have a value that makes the denominator 0, but the numerator is not 0, then that value is producing a vertical asymptote. And see, if we know it's a vertical asymptote, then we know the limit has to be positive infinity or negative infinity. So let's look at an example here. For the function 2x plus 4 over x squared minus 4, let's find the numbers that are not in the domain, and then determine the corresponding limit as the variable approaches those values. So you know the drill. Write this down in your notes because I'm going to head off to the chalkboard to work through this example. All right, as we just discussed, it's important to determine, or it's important to know when the graph's going to have a hole in it or a vertical asymptote. So in this example, we've given this function 2x plus 4 over x squared minus 4, and we're asked to find the numbers or the values of x that are not in the domain. And let's find the limits as the variable approaches those values that are not in the domain. So keep in mind, values of x that would make the denominator 0 are not in the domain of this function. So look at the domain, or look at the denominator. The denominator is x squared minus 4. What values of x would make x squared minus 4 0? That's right, negative 2 and positive 2. So there are two values of x that are not in the domain, negative 2 and positive 2. Let's analyze each one of them individually. So let's start by analyzing x equals negative 2. This is a value of x that makes the denominator 0. Notice that this value of x also makes the numerator 0. Put negative 2 in here for x. 2 times negative 2 plus 4, that's 0. So this value of x makes the denominator 0 and it makes the numerator 0. Since it makes the denominator 0 and the numerator 0, I know this value of x is producing a hole in the graph. And because it's producing a hole, it's just like what we saw in the last section in trying to find the limit. In trying to find the limit as x approaches negative 2, the first thing you would try is substitution. Substitution gives us 0 over 0. Indeterminate form, 0 over 0. So we know we have to do some algebra magic, which is factoring. The denominator factors to, what's the difference of two squares? So it factors to x minus 2 times x plus 2. And you know what? Why don't we go ahead and factor the numerator? We can factor a 2 out of the numerator. And now that we have everything factored, notice we can cancel the x plus 2's, which leaves us with the limit as x approaches negative 2 of 2 over x minus 2. We substitute, we get 2 over negative 2 minus 2. That's 2 over negative 4, negative 1/2. So the limit is negative 1/2. X equals negative 2 is producing a hole in the graph. The other value of x that's not in the domain, or the other value of x that we're going to analyze here, is the x value of 2. That makes the denominator 0. But notice that x value of 2 would make the numerator a positive 8. It's a not 0. So x equals 2 is a value of x that makes the denominator 0, but the numerator is not 0. That means this value of x is producing a vertical asymptote. So I now know that the limit as x approaches 2 from the left side of 2 and the limit as x approaches 2 from the right side of 2, I know this limit is either positive infinity or negative infinity because we have a vertical asymptote. And I know this limit is either positive infinity or negative infinity because we have a vertical asymptote. So what I would probably encourage you to do, we know the answer is either positive or negative infinity for these two. I would encourage you, use your calculator. Graph the function. And if you do that, you'll get a graph that looks something like, see, we've got a vertical asymptote at x equals 2, and you'll have a graph that looks something like that. So now I can immediately determine as I approach 2 from the left side of 2, that limit is negative infinity. As I approach 2 from the right side of 2, that limit is positive infinity. And then that tells me that the limit as x approaches 2 does not exist. Those aren't the same thing. So that limit does not exist. So to recap before we go back to the slides, a value of x that makes the denominator 0 is doing one of two things: producing a hole in the graph or producing a vertical asymptote. So if a value of x that makes the denominator 0 also makes the numerator 0, you have a hole in the graph. If a value of x that makes the denominator 0 makes the numerator not 0, you have a vertical asymptote. And it's that knowledge of a vertical asymptote that tells us if the limit is a negative infinity or positive infinity. But let's head back to the slides and see what's next.
All right, well, that wasn't too bad. Vertical asymptotes are our friend. So let's look at an application of these infinite limits. So this example, and again, write this in your notes. The city of Deaverville is interested in analyzing the cost involved in removing local water pollution. The cost of removing pollutants in Lake Kirkstand, that's near the city of Deaverville, is a function of the amount of money invested in its removal, and it can be modeled by C of x equals 93x over 100 minus x. Here, x is the percentage of pollutants removed,
And C of x is the cost of removing the pollutants, and it's measured in thousands of dollars. So here in part A, we're just going to do an old algebra problem. We're going to evaluate C of 40 and then interpret what that means. And then in part B, we'll determine the limit as x approaches 100 from the left of C of x and interpret. So here I go. I'm going to head off to the chalkboard and work through this example.
All right, this example we're going to do, we're kind of applying these infinite limits. I'm not going to read it to you again because you should have, written this into your notes. I just wrote down what the function was, and that is a cost function. I will say one more time that x represented the percentage of pollutants removed, and C of x is the cost, and it was measured in thousands of dollars. So part A, we're asked to find C of 40 and interpret. So C of 40, well, that's a 93 times 40 divided by 100 minus 40. And when I use my calculator, I get C of 40, I get this to be 62. Okay, now the interpretation part. What does this mean? And we're going to be doing a lot of this and interpret throughout this entire course. So let's talk about, it's just really when you interpret something, you're writing a short, sweet sentence. It's not a paragraph, it's not an essay, just a nice, short, sweet sentence. So what does this mean? Well, here, this means that the cost to remove 40%, that's what the 40 was, percentage, the cost to remove 40% of the pollutants is 62, and then we were told C of x is in thousands of dollars, so this is $62,000. That's it. That's the interpretation. A nice, short, sweet sentence. Okay, part B, find the limit as x approaches 100 from the left of 93x over 100 minus x. So I know 100 is a value of x that makes the denominator 0. The numerator is not 0. So I know we have a vertical asymptote at x equals 100. I also know that means that limit is either infinity or negative infinity. Doing a quick graph, and I used my calculator, and this is what I saw as a graph. Obviously this limit is positive infinity because we're talking about a cost. I wouldn't expect it to be going to negative infinity. So we know the limit as x approaches 100 from the left of 93x over 100 minus x, that limit is infinity. Now interpret this. What does this mean? Well, the 100 means we're trying to remove 100% of the pollutants. How much does it cost? Well, the cost is increasing without bound. Bill Gates doesn't have enough money to do this. So the interpretation would be to remove 100% of the pollutants it is, and I like this phrase, it's cost prohibitive. It would take an infinite amount of money. That means it's cost prohibitive. So there's an application of these infinite limits. So let's head back to the slides because next up we're going to start looking at limits at infinity. So let's head back to the slide and see what that's all about.
All right, next, objective 3, we're going to analyze limits at infinity and horizontal asymptotes. So limits at infinity, that just means we're going to let the independent variable, x, we're going to let it head off to infinity or head off to negative infinity.
So let's look at the following example. We're going to look at the graph of f of x equals x plus 1 over x. Here it is to the right. And we're going to use this graph to determine the limits. In part A, the limit as x goes to infinity, x plus 1 over x. And in part B, the limit as x heads off to negative infinity, x plus 1 over x. So as always, get this transcribed into your notes because I'm going to head off to the chalkboard and work through this one.
All right, in this example, you're asked, to use the graph of f of x equals x plus 1 over x to find these two limits. So I've reproduced the graph over there. So let's look at the first one. The limit as x approaches infinity of x plus 1 over x. So we're letting our independent variable x increase without bound. It's heading off past Bill Gates' bank account. What are those y values getting closer to? Well, as x heads off to infinity, it looks like the y values are getting closer and closer to that red dashed line. Well, that red dashed line is a horizontal asymptote. I'll abbreviate that, horizontal asymptote. And its equation is y equals 1. So it looks like when x heads off to infinity, those y values are getting really, really close to the horizontal asymptote, which is y equals 1. So this limit is 1. All right, now what happens when x is heading off to negative infinity? We're letting the independent variable decrease without bound. Those x values are heading well past the federal debt. What are the y's getting closer to? Well, again, it looks like as those y's head off to negative infinity, as the x's are heading off to negative infinity, it looks like the y values are getting really, really close to the horizontal asymptote, y equals 1. So it looks like as x heads off to negative infinity, the y's are getting closer to 1. And that's it for this example. So notice the connection between these limits at infinity, that when we let the independent variable go to infinity or negative infinity, notice how we used our knowledge of a horizontal asymptote to tell us these limits. So let's head back to the slides because we'll do a little bit of review from college algebra. How can we determine horizontal asymptotes? Because if we know horizontal asymptotes, then we know these limits very quickly. So let's head on back to the slides.
All right, as we saw in that last example, the line y equals 1, it was a horizontal asymptote. And the horizontal asymptote was key in helping us determine those limits. So for any function f, if the limit as x heads off to infinity or negative infinity of f of x equals L, then we say y equals L is a horizontal asymptote for the graph of f. So let's turn that around. In short, if we know a horizontal asymptote, we're going to know one of these limits at infinity. So knowing horizontal asymptotes will be key for us. So one quick little comment before we talk more about horizontal asymptotes. If n is a positive real number, then the limit as x heads to infinity of 1 over x to the n equals 0. And if n is a positive real, the limit as x heads to negative infinity is also 0, provided, of course, x to n is a real number for negative values of x. So the key in finding these limits at infinity, there's going to be a strong connection to horizontal asymptotes. So in college algebra, we would have seen how to determine horizontal asymptotes. And we can use our knowledge of horizontal asymptotes to find these limits at infinity. So let's review from algebra how we can determine horizontal asymptotes for a function. So the first thing,
all of this is going to revolve around the degree of numerators and denominators. So first thing, if the degree of the numerator is less than the degree of the denominator, then the line y equals 0, also known as the x-axis, is the horizontal asymptote. Please remember that degree is the largest exponent that you see. If the degree of the numerator is greater than the degree of the denominator, well, then we don't have a horizontal asymptote. You may remember from college algebra, you have something called a slant asymptote, but we're not going to concern ourselves with that in this course. And then the third thing is if the degree of the numerator is equal to the degree of the denominator, then the horizontal asymptote is the ratio of the leading coefficients of numerator to denominator. So that you probably remember from college algebra. So let's see how we can handle this information with an example. So there's a function, f of x equals 4x squared minus 7x plus 1 over 3x squared minus 5. So let's find the limit as x heads to infinity of f of x and the limit as x heads to negative infinity of f of x. So I'm going to head off to the chalkboard to work through this. Make sure you write it down. So here we go. All right, folks, in this example, we were given the function f of x equals 4x squared minus 7x plus 1 all over 3x squared minus 5. I wrote it down over here. And we were asked to find the limit as x goes to infinity of the function and the limit as x goes to negative infinity of the function. Well, as we've seen, finding these limits at infinity, the key is, can we find the horizontal asymptote for the graph? So I look at the function. Remember, the key is degree of the numerator and degree of the denominator. So the degree of the numerator is 2, and the degree of the denominator is 2. So remember, when the degree of the numerator and degree of the denominator are the same, the horizontal asymptote is the line y equals the ratio of leading coefficient of numerator over leading coefficient of denominator. Well, the leading coefficient of the numerator is 4. The leading coefficient of the denominator is 3. So the horizontal asymptote is y equals 4/3. That quickly tells us that the limit as x goes to infinity of the function is 4/3, and as x goes to negative infinity, the limit is 4/3. So knowing the horizontal asymptote, we just immediately were able to determine these two limits. So to make sure you have this under control, I do want you to practice a couple of them here. So in the section 2.2 exercises, I'd like you to try numbers 26 and 28. So, you know the deal, pause the video. Section 2.2 exercises, do 26, do 28, then restart the video. I'll be here at the board working through them, and hopefully you'll have them correct. All right, folks, let's see how you did in 26 and 28. Number 26, you were asked to find the limit as x approaches negative infinity of 3x squared minus x plus 2 all over 2x squared plus x minus 5. So again, I'm looking for the horizontal asymptote. So when I look at the function, I see the degree of the numerator is a 2. The degree of the denominator is a 2. That's the same. So that means the horizontal asymptote is the line y equals leading coefficient of numerator over leading coefficient of denominator. That immediately tells me that this limit is 3/2. That's it. Done. 28. To find the limit as x goes to infinity of this function. I attack it the same way. I'm going to look for the horizontal asymptote. So for this one, the degree of the numerator is 2. The degree of the denominator is 3. Remember, when the degree of the numerator is less than the degree of the denominator, the horizontal asymptote is the x-axis, also known as the line y equals 0. That immediately tells me that this limit is 0. So that was it for 26 and 28. I hope for 26 you got 3 halves, and I hope for 28 you got 0. So let's head on back to the slides. I'm sure we're going to now look at an application involving these types of limits.
All right, as we saw in that example, and the couple problems that I asked you to do following the example, the ability to find a horizontal asymptote makes finding those limits pretty friendly. So let's conclude this section with an application of limits at infinity. So the local game commission has decided to stock Lake Gloucester with 200 trout. Now, the subsequent population of trout in the lake can be modeled by P of x equals 20 times the quantity 10 plus 7x, and then all of that is over 1 plus 0.02x. And that in this function, x is the number of months since the lake was stocked, and P of x, well, that's the trout population. So we're going to do a couple of things here. In part A, let's just determine the trout population 1 year after the lake was stocked. And then in part B, let's determine the limit as x heads to infinity of P of x, and let's interpret that. So again, make sure you write this down, have it in your notes, because I'm heading off to the chalkboard to work through it.
All right, this example was an application. I'm not going to read it because you should have written this down into your notes like I asked you to. I'm just writing down what the function was. P of x was 20 times the quantity 10 plus 7x, all over 1 plus 0.02x. I did take the liberty, because this is something that will be important to do, to rewrite the function by just distributing the 20 in the numerator. Keep in mind, x represented the number of months since this lake was stocked with trout, and P of x is the population of trout. So part A, determine the trout population 1 year after the lake was stocked. That means we need to evaluate this function at 12. X represents the number of months. So 1 year would be 12 months. So I put 12 in for the x's, and I would use my calculator here. And when I use my calculator, I get a 1516.129. Okay, but folks, we are talking about trout. Don't say the population of trout after 1 year is 1516.129. I don't know what 0.129 of a trout looks like. So let's just round it to the nearest whole number. And let's just say the population after 1 year was 1,516 trout. Okay, part B. Determine the limit as x goes to infinity of P of x, and interpret. Well, this is where it was helpful for me to distribute the 20. Because when I look at the function now, I see the degree of the numerator is 1. The degree of the denominator is 1. Since the degree of the numerator is the same as the degree of the denominator, I know the horizontal asymptote for the graph is the line y equals leading coefficient of numerator over leading coefficient of the denominator. So it's a 140 over a 0.02. And if I take 140 and I divide it by 0.02 on my calculator, I get 7,000. Since I know that, I immediately know that the limit as x goes to infinity of p of x is 7,000. So now what does this mean? The interpretation, what does it mean? It means, there are several ways biologists represent this, several different phrases. I'll write down one of them and mention the other ones. But it means that the limiting size of the trout it's 7,000 trout. So that means as time goes on, this lake, as you go as far into the future as you want, the number of trout in this lake will not go beyond 7,000. So some biologists, they do call it the limiting size. Some call it the carrying capacity. And they would say the carrying capacity of the trout is 7,000, trout. So limiting size, carrying capacity, either of those fine. I mean, if you were to say your interpretation is, as the number of months increase without bound, the population of the trout is 7,000, that's fine. I just thought I would toss in a couple of biological terms here, limiting size or carrying capacity. But that's it for this example. So what I'd like you to do right now, I'd like you to go to the book, section 2.2 exercises. I'd like you to try number 45 to practice this and see what you get. So do number 45, pause the video, do number 45. Once you've done it, restart the video. I'll be here at the board working through the solution. All right, folks, here number 45. Let's see, there were a lot of words. You probably read them. But you're given the function n of x equals 2,000 minus 520 over x. Here, x represented the amount spent on advertising, measured in thousands of dollars. And n of x represented the number of cases purchased. So we're asked to find the limit as x heads to infinity of n of x and interpret. Well, so the first thing, let's get this limit. A couple of things embedded in here. First, the limit as x goes to infinity of 2,000 is 2,000. Remember, the limit of a constant is a constant. Second, the limit as x goes to infinity of 520 over x, well, that's 0. Because if I think of it as the horizontal asymptote, what's the horizontal asymptote for 520 over x? Well, the degree of the numerator is 0, degree of the denominator is 1. There you go. The horizontal asymptote is y equals 0. So this limit is 2,000. So now what does that mean? Well, as x is approaching infinity, now x represented the amount of money spent on advertisement, so I would start off by saying as the amount spent on advertisement, I'll just abbreviate that to ads, as it increases without bound. The number of cases purchased, remember n of x told us cases purchased, so the number of cases purchased is 2,000. So as you spend more and more money on advertisement, as it increases without bound, goes beyond Bill Gates' bank account, boom, number of cases purchased is 2,000. So, all right, that's it for section 2.2, folks. That's everything in the section. So at this time, you can go ahead and do the exercises in section 2.2. Thanks for watching.